Hey, everybody. There was a question that I got several questions about. So I just want to make a quick example of a similar kind of question. So here's a couple of functions. F of x is 10 minus x squared. G of x is x cubed minus 2. I've got them graphed over here. And it's pretty quick to see they intersect at 2, 6. And let's answer this question. What is the angle between the curves at this point? Okay, so the way we'll think about this, I mean, there's actually quite a few things we should have to ask ourselves, but when we say the angle between these curves, what we're going to think about is the direction of their tangent lines and the angle between the vectors that go in those directions, right? So if I have a curve like this and another curve like this, if this one has tangent vector this way and this one has a tangent vector in this direction, then what we would think about is, oops, let's do this. What's the angle between those two vectors? Okay, so then once we get their vectors, we can forget the curves and just look at the direction, the angle between the two vectors, right? In this case, it would be this vector theta in here. Okay, so that's the idea. So we look at these two curves and we want to think about the tangent line to each curve and what direction that tangent line is moving in. So let's find derivatives, right? And I guess this is one of those things that I think we often forget what it means because we're so used to using it. When you find a tangent line or any line, there's two pieces of information you need. You need its slope and you need any point on it, right? So we often talk about the intercept, but we can make this more general. If you look at the point slope form of a line, if you take y minus y naught equals m times x minus x naught, right? X naught, y naught is some point on the line and m is the slope. If you have those two pieces of information, then you'll have the tangent line. In this case, we know both of the tangent lines are going to have the form y minus x equals the slope of their particular curve at that point times x minus 2, right? Well, the slope gives us the direction of a line, right? So we think of it as this number. We know it's related to steepness, which is direction, but we're going to think a little bit harder about what that means now and try to connect it to vectors. So let's find these two slopes and then see what that means as a vector. So for f of x, the derivative is just negative 2x. So the derivative at 2 is going to be negative 4. G of x has a derivative of 3x squared. So g prime at 2 is going to be 12. All right, so I could easily write down now the two tangent line expressions. We'd have y minus 6 equals negative 4, x minus 2 for f. We'd have y minus 6 equals 12, x minus 2 for g. But what do those slope numbers mean? Well, let's come over to this graph and graph those tangent lines, or at least a portion of them. And I'll say why I'm only doing a portion in a second. So there's my two tangent lines. And let me even change my window here. Let's stretch out the x values a little bit to make this a little bit clearer, I hope. Let's do it even more. Okay, so now I'm zoomed in on that point, and you can see I have not graphed the entire tangent line, but I've just graphed a portion of each tangent line. So the purple one is a portion of the tangent line for G, and the red one, the orange one is the portion of the tangent line for F. Okay, so let's look at F, whose slope is negative 4. What does a slope of negative 4 mean? a slope of -4, right? M equals our slope. One way we can think of it is delta y over delta x, right? What's the ratio of changing y and a change in y and a change in x, right? Well, -4, we can think of it as -4 over 1, which is a way of saying if you change x by 1, y will change by -4. Right? It's a ratio. So if you change x by 7, then y would change by -28, but it's still in that ratio of -4 to 1. Every unit change in x yields a -4 unit change in y. In this picture, so my scales for my x and y are not the same here, so it doesn't look like what I'm about to say, but if you look at the grid, oh yeah, let's just put the grid up. That'll be easy enough. Where's my grid? Okay. Yeah, these are grids by 1. You can notice that as we change x by 1, let's make this thicker. If we change x by 1, I don't know how to make it thicker anymore. I used to know that. Anyways, if we change x by 1, move over 1, we're going down by 4. Well, as a vector, that is a vector that goes over 1, down 4. That's 1, -4. I'm thinking in 2 dimensions right now. So the vector equivalent of a slope of -4, I'll call this vector, we'll just call this one u, is 1, -4. For our purple graph, right, very similar thing. The slope of 12 means we go over 1, we will go up 12, right? So the reason I graphed only a portion of those tangent lines, I graphed the portion that was 1 unit increase in x so that we could connect it to this idea of vectors, right? So let's put that over here. So our vector corresponding to a slope of 12, I'll call it v, is a vector 1, 12, right? It doesn't matter that x is equal to 2. This component here, the 1, has nothing to do with where we are on the graph. It has everything to do with how the graph is changing at that point, and that's given by the slope. A change of 1 unit in x yields a change of 12 units in y. It's not about where we are, right? I know several people were confused about the fact that how come x isn't 2 since we're at x equals 2. This x component is not telling you where you are, it's telling you how you change, right? Vectors tell you where to move in the x and the y, right? But vectors can be located anywhere. I could move this vector to the origin, I can move it off wherever I want. The vector itself still moves over 1 up 12 or over 1 down 4, depending on which one we're talking about. So those are the 2 vectors that we're talking about. Let me clear everything here, right? If we now ignore the graphs themselves, whoops, wrong button. Let's get rid of the functions here. Let's get rid of this grid. The question is now, what's the angle between these 2 lines, right? The angle between them. And we know how to solve that. Let's do that work. We know that if we take u dot v, we get the magnitude of u times the magnitude of v times the cosine of theta, the angle between them, right? The angle between 0 and pi, between them. And we can solve this to get that theta is equal to the inverse cosine of the dot product divided by the product of their magnitudes, right? And this should give us the angle. So in this case, the dot product, let's just figure this out quickly. The dot product, 1 times 1 plus -4 times 12 gives me -47. The magnitude of u is the square root of 1 plus 16, or root 17. The square root of v is the magnitude, is the square root of 1 plus 12 squared, or root 145. So the theta we're looking for is the inverse cosine of negative 47 over the square root of 17 times 145. We can plug this in. I've got Desmos open. Let's use that. Whoops, keep hitting the wrong thing. We want cosine inverse negative 47 square root of 17 times 145. So we get let's go to 3 decimal places, 2.813 radians. Okay, so that last part, just some simple computation. The important thing here is this connection between slope and vectors. It helps us understand better what slope is. It helps us understand better what vectors are too, I think. And so we want to have this real geometric picture of vectors, these objects, right? I presented over here on the graph these as portions of the tangent line, but we can really just think about these now. Oh, there's my thick line. We can really just think about these as vectors. What I was really drawing was a vector. This was the vector I called, which one was which? Oh, this was V. And this was the vector U. And we found theta between them to be approximately 2.813 radians. Okay. Okay, that's it for this one. Thanks, everybody. I will see you next time.